Hi, I'm Madison Sofield, and today is our newest episode of the Expert Forecast. Today I'm here with Sam Gagnar. Could you introduce us and tell us a little bit about what you do at tomorrow.io?
Sure thing. Yeah, so I'm the Director of Mission Operations at Tomorrow.io. I've been here for a number of years now, and my background is in satellite operations, dating back to some time I spent working a lot of NASA missions at CU Boulder. And I also have a background in mission planning and scheduling and some onboard flight software. At Tomorrow, my biggest focus is working on our microwave sounder constellation, which we've been growing for the last few years. And largely, the mission operations team is focused on the day to day upkeep of those satellites, maintaining the performance of the satellites and the payloads, continuing to collect important weather data that's important for our forecasting platform, and just keeping that moving day to day. So we send information up to the satellites on a daily basis, receive the data downlink from the satellites on an ongoing basis, and our job is to get that data to our science team and our weather team to support our product.
Awesome. All right, so let's get right into it. We have some great questions for you today. So I want to first ask you, the space industry is evolving very quickly. From your perspective on the mission operations side, how is the landscape of weather satellites and space infrastructure changing today?
Yeah, I think we're seeing a lot of opportunity in the commercial sector to provide impactful weather observations from space. Like we're seeing that we can launch and operate a large number of relatively inexpensive, but still highly capable satellites in low Earth orbit. And this provides an effective complement to larger government weather satellite programs. And in terms of operations, from my perspective, what we're seeing for a while now is a shift away from single satellite operations to more of a constellation or a fleet management approach to operations. One term I heard recently is sat DevOps, which I think captures how we're operating our payloads and where I see mission operations going as a whole, not only for us, for the industry. Satellites are becoming more interconnected with ground systems, interconnected with other satellites. And so operations is starting to look a lot more like maintaining, you can think of them as compute nodes or even servers that just happen to be in space, which is a bit of a paradigm change. And I think it's been happening for quite some time now. And it's very exciting.
Tomorrow IO has a very different mission compared to traditional space weather programs, like you're mentioning. And how does our approach to space and weather data change what's possible for forecasting on Earth?
Yeah, I think we're different in that we have a very clear goal, which is to improve weather forecasting and provide predictive insights to our customers. So this shapes how we operate really from the ground up because we care very specifically about how quickly we can deliver global observations to our customers and data products in various ways. So yeah, we use ground stations all over the globe, 20 plus ground stations strategically, and we strategically schedule contacts to reduce the data latency, which is the time between the observation is taken and the time when the data is available to our platform. And so that really kind of core mission goal to serve our customers or our platform shapes everything that we do, and it gives us a lot of really clear direction in how we operate.
Yeah, yeah. From understanding of like different businesses that we work with, if it's like sports or like stadiums, we kind of are able to combine that like ground radar with space radar, which I know is really unique. Yeah, so thank you for that context. I would love to ask you some questions more specifically about satellites and what they do because you're in our space team. And I think a lot of people are curious about like what's happening up in space. So, for the people who may not be familiar, what exactly are the Tomorrow IO sounder satellites designed to do, and why are they so important as part of improving weather forecasting?
Yeah, the Tomorrow, these sounder satellites use it's a passive microwave sensor, a radiometer, and we use it to measure. It measures the natural emissions from the atmosphere at specific frequencies, really a range of different frequencies. So from these measurements, scientists can retrieve what are basically vertical profiles of temperature and moisture in the atmosphere, essentially a slice of the atmosphere.
Mhm.
And because these instruments have a very wide collection area or swath, with a constellation of 20 or so satellites, we can provide really frequent global measurements to input data into these weather models, which then can provide more accurate picture of the atmosphere for improving forecasting accuracy. And so the combination of sort of that wide collection area and with the number of satellites operating in low Earth orbit, we get that coverage and we get that really frequent data delivery through those ground station contacts that I mentioned.
When you think about operating a constellation like this, what makes it fundamentally different from traditional satellites or missions?
Yeah, so yeah, there's a whole lot of different ways to operate satellites, and every mission is different. But when I started my career, I was working mostly with satellites that required humans sitting on console, basically to kind of manually uplink commands or instructions to the satellite or uplink files multiple times per day. But really, a human kind of directly in the loop to keep the missions running. Traditionally, is kind of how things have been done on various levels. And yeah, with us, we still rely on commanding, of course, but the satellites I've worked on over time have gotten better at operating autonomously. Um, so really, what that means is that any commands we send, they can help optimize our operation or kind of hone in on the high value operations or data collections, but they're not necessarily like critical to day to day payload operation. So like what I think is traditional has been constantly evolving really more towards automation for a while now. I think what makes our sounders a bit unique is that we're trying to achieve a highly autonomous and robust operation, but at a significant fraction of the cost with a small team. So significantly less expensive and smaller than a traditional weather satellite program. And I'll say it's, mission operations is just one small piece, but the ability to continue to build and deploy satellites like this is a very hard problem in itself. And so our ability to roll out these satellites kind of on an ongoing basis and continue to build and really maintain this constellation of small satellites is not a trivial task, and is impressive from my perspective. Like seeing just kind of the end of it as a mission operator, it's really just like the end of a much larger process to keep this all going, which is really cool.
Very cool. It's super unique. All right. I would like to talk about a story that you shared with me that I'd like to share with everyone that I thought was really interesting. So, I want to talk about our S1 satellite. Early in the mission, the team encountered issues communicating with the payload. Can you explain how this impacted operations and the impacts of the overall mission? And maybe also like a little bit of background about that satellite and what is a payload? I think for people that don't have all of the background too, would be great.
Yeah, for sure. So these payloads, this radiometer payload is very capable payload, but it's a relatively simple operation. It's kind of collecting data all the time. These satellites I mentioned coverage, we're constantly running. We're trying to collect as much data as we can over as much of the globe as we can. So the operation itself is fairly simple, but it still requires commanding to configure the payload at startup, get the system configured with all the right parameters to be able to collect the data properly. And it also requires periodic commanding to kind of calibrate the payload, which happens once per rotation. The payload is revolving. And when we started having problems with the payload, it was a communication problem. We're having trouble communicating with the payload. And the biggest impact there is dropped commands, because without those, we couldn't get the payload into a normal operating state. And then you can't really produce the operations that you need. The hardware was fine, but we couldn't set it up to do data collection like normal. So it's kind of a frustrating thing, right? You have this perfectly healthy payload, at least seems like a perfectly healthy payload, but you can't make any use of it because you can't talk to it. And so that
Mm,
was kind of the fundamental challenge here was what can we do to keep this thing going? Like we know it's healthy, but we can't produce the data.
yeah. All right. So when missions start having problems like this, what does that moment look like from a mission operation standpoint? What are you guys doing?
Yeah, it's never fun to have issues with space hardware, mainly because it can be really challenging to debug problems. You can't just get in there, run debug tools, go into the system, look at files like you would on the ground. We have limited time windows in which we can communicate with the satellite. Fundamentally, it's over ground station contacts, which are relatively short. We have a lot of them, but you're still kind of time constrained there. And so the other aspect of this is, since the fundamental problem was communication, we might not be able to get the data we need to debug in the first place, right? Because we can't actually get in there and prod without that communication channel. So that could be really, really frustrating for both our engineers within our systems engineering team, who have the technical insight, and of course our operations team who are trying to understand the root causes. So, in this sort of situation, it looks like a lot of frustration, a lot of uncertainty at first, which is part of the process here. But yeah, it can be a real challenge.
So then I would love to understand more about how you responded to this problem. So I know that the team tried several approaches to recover payload operations. How did you decide what to do to respond to these problems? And what did you learn during those recovery attempts?
Yeah, so we had some heritage on this payload that gave us a good starting point. A lot of payloads in space have systems they inherit from. In this case, we kind of evolved from a prior NASA mission, payload on board a NASA mission. And so but we found out pretty quickly that our system behaved differently from some of those heritage systems. Every system is different, every satellite's different, every payload. And so we're kind of paving new ground. The most important thing is to try to break the problem down systematically, just really like any fault review process, which is common in engineering. We learned that there simply weren't a lot of things we could really directly measure. I mentioned that we were having problems communicating with the payload, which gave us a pretty limited tool set to work with. We're a little bit hampered because we didn't have that communication channel. But we knew that we could start really simple with like the simplest possible diagnostic steps, turning the payload on in the lowest possible mode, and just working our way up from there. And that provided a good starting point. And certainly it was a learning opportunity, not only in terms of what we were starting to see from the payload, but also a learning opportunity for how to apply and define these processes moving forward.
Yeah, I bet, right? Like when you're learning about these things, there's a lot of unpredictability, I feel like, when it comes to space. And right, we have to learn how to adapt. So I bet there's a lot of learning for you and the whole team in this process. Um, all right. So at one point, it appeared that communications with our payload were completely ineffective, which was like, I imagine, not good. Yet the team continued testing and iterating. What kept the team pushing forward rather than treating the satellite as a total loss?
Yeah. So one thing that helped was knowing the payload itself. Like we were pretty confident the payload itself was still fully functional. And what I mean by that is that this radiometer, which is kind of a self-contained unit that takes all these observations, that was fundamentally still working. And the problem was we just had this issue with the communications kind of to and from the payload. And so we knew that if we could improve the communication, or if we could at least solve or improve that one particular piece of it, that would translate to some amount of operation, right? Even if just partial. And so we felt like this wasn't something we just throw in the towel because we had all these things telling us that the payload probably could still provide value. We also wanted to learn as much as we could from the issue just so we could apply that knowledge to other satellites. Even if you can't recover something fully, you still want to understand how to mitigate it and how to avoid it as best you can in the future. And so whenever you have issues like this, of course, you're thinking that this could result in, if not a serious degradation to the mission, potential loss. All satellites eventually have an end of life, and you don't want that to happen sooner rather than later. But also looking holistically, we need to look at this as a constellation. Like we're going to maintain the performance of these systems in the long term, right? And all these satellites have the same payload. And so we need to learn as much from this experience as possible, even if the payload isn't going to work. What information, knowledge, and process can we gain from that to make sure that we can apply that to the future missions, which is obviously critical.
So now that you've mentioned that there was a lot of learning that came from recovering the S1 satellite, I would love to understand a little bit more about like why we're talking about it today. Like why is it so important and such a big deal that we were able to recover the S1 satellite? Eventually the team developed a new flight software and operational procedures that brought the S1 satellite back online, which is awesome, and was producing data again. What did that recovery mean for the mission and the team?
The short answer is it means a whole lot. It means a whole lot to the team and the company when you can come out from these issues and still have a good path forward, right? You're not throwing in the towel, like I said. So, our team did an amazing job coming up with some clever adjustments. You mentioned the flight software. Really, we're making some kind of tweaks to software to significantly reduce how much of that commanding was necessary to operate. So, really looking at again the problem being the communications. What can we do to not necessarily solve but mitigate what we have available to us, which is a reduced communication channel. So this update not only did it restore data production for this satellite, which means we're continuing to flow data to our forecasting platforms, data available for the scientific community, things like that. for this particular satellite. Maybe more importantly, it gave us, again, this response pattern that we can use for other satellites in the constellation, both now and in the future. Really, instead of having a failure mode with drastic implications, potentially mission-ending implications, uh, highly uncertainty, a situation with a lot of uncertainty, like I mentioned, instead of that, we have now a quantifiable risk with a known mitigation plan, which is a huge difference. And it makes a big difference for the operations team, of course, because we feel like now we've restored control, right? Our jobs are to
Yeah.
maintain the performance of these systems. And now we have a tool set to be able to do that more effectively given this known failure.
Yeah, exactly. It's like there's so many wins in it. It's like we've got the S1 satellite back, which is awesome, and it can continue to provide that data that's essential and it's covering major gaps. But also, we learned so much from it. Like, how many satellites after that did we launch, right? And how many can that
Mm-hmm.
affect in future launches is really impactful. So it was really great to see that your team was able to recover it. I would like to ask now, looking back now, what does the recovery of S1 say about the resilience of the mission and the way Tomorrow approaches building and operating space systems? Is, expanding on the idea that there was a lot to learn from the recovery of the satellite.
Yeah, I mentioned it's obviously a big thing for us as a team and as a company to keep these things operating at the high level of performance that they are. It's a huge learning experience, of course, and really a growth opportunity for the mission operations team to go through things like this. You mentioned resilience. As operators, our jobs often involve reacting to problems like this and finding novel solutions. It is kind of part of our job is to be reactive, right, as operators. But we also want to be as proactive as possible to reduce problems in the first place, or at least reduce their likelihood. And as I mentioned, also have a well-informed process or set of processes in place for handling them when they do occur. And so all that is really, really important growth for us just as a team and as a company with these payloads, but also looking towards future payloads. So we want to build a resilient program, especially given the types of satellites we're operating and building and how rapidly we're growing. And so it's really important to have that. And I think this was a huge learning step.
Yeah. And I like what you said about being proactive and reactive, because I think even though the space and the weather team are working on very different parts of what is the whole of tomorrow, it's very consistent that the point of why we're doing all of this is so that we can provide things for, countries, right, or businesses to be incredibly proactive about weather, to protect themselves or others or their business, but also to be reactive. Like when things happen, they can act upon it. And I think it's great because it shows this bridge of really overall what we do at tomorrow. It's really about creating that resilience for businesses, but it comes from the fact that we start with that within internally, which I think is really cool. See that kind of pattern throughout the different segments of the space mission to the weather modeling that we do. All
Yeah.
right.
Actually, one thing I can say, Madison, is yeah, I mentioned mission ops is kind of one piece, but we're really trying to grow in terms of resilience, like an end to end system, right? Satellite, all the way down, satellite through the ground stations, through our data processing platform, to our products and to our customers. And so I kind of use the sat DevOps term. In a lot of ways, it is that, right? It's a combination of, not just reacting and fixing the problems, really building these resilient systems to illuminate when problems are occurring, when performance isn't up to spec, and then having people who are kind of like on the loop there, working with these systems and keeping them running as efficiently as possible at scale, which can be a huge challenge, of course, with a small team, but that's why you need those resilient platforms.
Looking ahead, how are the lessons from the S1 satellite shaping the next generation of tomorrow satellites? And is it including our upcoming deep sky constellation?
Yeah, for sure. All these things we're talking about really apply directly to the future. As we move towards deep sky, we're talking about a lot more complexity to deal with from a mission operations perspective and really a data processing perspective in a lot of ways. And so, as we grow our constellation, add these different, add functionality in terms of additional payload types, having those strong methodologies like we were talking about for identifying and solving problems or solving performance deficiencies is going to be absolutely crucial for the business. Like I was talking about automation, we need to build automated systems and processes that are even better at recognizing any change to performance and making things as transparent as possible for the operations team and anyone, really anyone on the loop, right? In the loop all the way down from operations through data processing, the whole stack. We need as much transparency as possible. And the reason that's important is because you have to empower the mission operations team to make informed and potentially quick decisions, right? And not only timely decisions, but also the ability to act confidently when things are going wrong, to keep things running smoothly. And having that information transparently, it's not necessarily an easy problem to solve, but as a mission operator, you really want to feel empowered to solve those problems and have clarity in the midst of problematic situations. And so, yeah, I expect with Deep Sky it's going to be a step up in complexity, but I think we're setting a really good foundation here with our current generation. All of it's an evolution towards bigger and better things.
Definitely. We did the first constellation and now it's off to the next one, and we're so excited about it. All right. And the last question I have for you is on a personal level. What did working through the S1 recovery teach you about operating in space and being a part of a mission like this?
It's always it's always a rewarding experience to find ways to succeed, like through any kind of adversity or problems like this on orbit. In a lot of ways, having opportunities to solve these types of problems is why people who work in mission operations enjoy what we do. Right, you're kind of the first line of defense, working with the satellite hands on, so to speak, right, which can be very exciting, but also stressful, right? You're dealing with these problems,
Mm,
you're dealing with the uncertainties and things like that I mentioned. Really for me, I've been through a number of different missions and experiences like this. But for me, this is a really positive experience here just to see how far Tomorrow has come in
mm,
such a short time with these satellites. How well they continue to perform despite these types of issues is really just a testament to the whole team at large, right? All the engineering and time that went into making these things work as well as they do. And to me, paints just a really positive picture for how much more we can do in the future. So, like going through these problems, yeah, it's a step. It can be rewarding or vindicating in a way on a personal level because we're keeping it going and we're contributing to the this constellation. But I see it again as just another step forward in this amazing kind of growth opportunity we have here tomorrow IO to build this weather constellation and this next weather generation weather constellation.
yeah, yeah, definitely. Well, I want to say thank you so much for taking the time to speak with us today and give us a little bit of a inside scoop of what it takes to recover a satellite, what goes into mission ops at Tomorrow for all of our, satellites up in constellation and for the future of deep sky. So thank you very much, and we appreciate your time.
Thank you too. I appreciate it.
Awesome.